Hello everyone and welcome back to Reservoir 2, PGE 323L. Again, my name is Matt Balhoff. So what we're going to start out by talking about is actually a continuation of primary recovery. But it's a really good segue into secondary recovery because secondary recovery is all about injecting artificially new fluids, usually water, and we call that water flooding, to produce more oil. The aquifer models is a natural drive mechanism, so it's still part of primary recovery, but similar in nature because it's water that's displacing the oil and is being produced. And what I have here is sort of a cartoon schematic of what that looks like. So of course we have our wellbore, which is in the center. We have our reservoir, which is on the outside. And yeah, it looks like a circle or a cylinder. We know real reservoirs don't look like that, but it's a really good analogy, and we can often make that approximation, or we can make a transformation to do that. So we have the reservoir, which is where our oil resides, as well as some water, as well as gas. But then there's often an outer region, an outer cylinder, if you will, that is a porous rock, but is filled with only water. And what happens is as we start to produce fluids from the reservoir, through the wellbore, the pressure in the reservoir, the red area, decreases. And when that pressure decreases, and you still have a high pressure in the aquifer, that water is driven into the reservoir. So that water pushes the oil, and then the oil goes towards the wellbore. So that's what happens with an aquifer and aquifer models. So now given that, a little bit of an introduction. So this maybe is a repeat of some of what I just said, but there is a drop in this reservoir pressure as you start to produce your fluids, oil and maybe some gas and water. And then the aquifer water expands and invades the reservoir. Sometimes we say it encroaches the reservoir, and that water pushes the oil towards the wellbore. So it's a natural additional drive mechanism for flow. Our goal is to develop a model, so some sort of mathematical model that predicts the cumulative amount of water that gets encroached from the reservoir, from the aquifer to the reservoir. And we're going to call that WE. Okay? You should recognize this from Reservoir 1, from the material balance equation. WE was one of the terms in there. At least when I teach the class, I don't do a whole lot with WE, mostly because we don't talk about aquifer models, but here we will. And it is in the material balance equation. One important thing is that we actually have more uncertainties in our aquifer than we do in our reservoir. And by uncertainties, I mean things like the permeability, the porosity, the thickness, variables like that. Now, why is that the case? Well, to know our properties, we have to do some work. And usually that involves drilling a well and either doing things like formation evaluation, and the majority of you are in formation evaluation this semester, so you're going to be learning about well logging and techniques to determine thickness and porosity and permeability. And then another way we do it is also through a well, is we collect a rock core sample and we bring it up to the surface, then we do experiments on it. Well, here's the thing, with reservoirs where we're making money and where we have oil and gas, we drill wells anyway. And so when we're drilling a well, it's easy to do our well logs, it's easy to get our core samples. In an aquifer, it's going to be really difficult to convince your boss that you want to drill a well in an aquifer, which is going to make no money because you want to know what the porosity is, right? Your boss is going to laugh at you, right? And if you're lucky, he or she might fire you. But if you're lucky, you'll get laughed at for wanting to spend several $100,000 or $1 million on a well so you can determine the porosity in an aquifer. So because of that, like I said, wells are not usually drilled into aquifers. There are exceptions. Therefore, things like permeability, porosity, thickness are not known very well. Compressibility of the water. The geometry of the aquifer is often not known. And so what we often do is we might assume that the same properties of the reservoir apply for the aquifer. So there's the same thickness, the same porosity, and that may or may not be a good assumption. But there is another procedure which is called history matching, which means that we make our prediction, then we start to produce fluids, and we see if our model matches what we're actually getting out. And if we're not, we tweak the model to match our actual production. So we call that history matching. So let me talk a little bit about some conceptual views of aquifers. The first one is going to be the one we use the most, and that's a radial aquifer. And in that case, you kind of have a circular reservoir and then an outer circle or cylinder, which is the aquifer. And most of the time, I'll actually use R sub E, not R sub O, for the radius of the reservoir, and we'll use R sub A for the radius of the aquifer. You can imagine that there's a direct analogy between this geometry and the geometry you learned last semester, where you had a wellbore. I like to use a roll of paper towels as a good analogy for a wellbore and a reservoir and maybe an aquifer. So you've got your wellbore in the center where you produce your fluids, and the outer reservoir. Well, the analogy is exactly the same there, except now the inner cylinder is the reservoir and the outer cylinder is an aquifer. So any equation that you learned last semester for flow from a reservoir into a wellbore is immediately applicable for flow from an aquifer into a reservoir, right? Because the geometries are the same. There's also models where you have a linear aquifer, so you've got flow coming from the side into the reservoir, or a bottom drive aquifer where the aquifer is at the bottom and kind of encroaches upwards. The equations that we'll use are most directly applicable to the radial aquifer, but they can be utilized for these other types of geometries in general. So moving forward, I would just assume that this is the type of geometry we're doing, and do know that we could apply our equations for these other geometries if we needed to as well. I should stop you at any time. Are there any questions about any of this?
You said that the equations that we used last semester also apply. I remember one of the assumptions that we made was that the wellbore was very small compared to the reservoir.
Yeah.
In this case, wouldn't the aquifer and the reservoir may be similar sizes?
Yeah, that's a really good question. So the question is basically the wellbore is very small, which it is. It's usually a few inches in diameter compared to a reservoir, which might be hundreds of feet in radius. An aquifer usually is a lot bigger than the reservoir, but maybe not to that degree. What I will say is this, is that the fundamental partial differential equations are the same, but maybe some of the boundary conditions or some assumptions we use to solve those PDEs are different. But sometimes they are directly analogous. But that's a really good point, because the reservoir, the wellbore is very small compared to the reservoir. It's not nearly as much of a discrepancy for the aquifer. Here is another view of the aquifer in the reservoir. This is a radial, so I'll go back. This is a radial aquifer, so you got the inner cylinder and an outer cylinder, except it's not a full cylinder. You have a sealing fault. So it's really like part of a cylinder, right? And you've got maybe some angle theta here, which is less than 360 degrees. So we have to account for that somehow, right? Because it's going to be less volume of the aquifer, less water encroached. So what we'll do is we'll introduce this dimensionless factor, F, which is the actual angle divided by 360. So if theta were 360, then you'd have a full cylinder, and then F would just be 1. If theta would be 0, then that would be not even there, and then you'd have F is equal to 0. So F is going to be somewhere between 0 and 1. If the aquifer is not a circle, we have to give an estimate of our radii, right? So you can imagine that the area of a circle is pi r squared. So what we're going to do is we're generally not given the radius of our aquifer or reservoir. We're usually given the area. And so we could say the outer radius, RE, is the square root of the area of the reservoir divided by pi f. And then the radius of the aquifer is the square root of the area of the aquifer divided by pi f. Because again, area is equal to pi r squared, so that's why we have our square root in there. And then we're accounting for this fact that it might not be a full circle, so we have our factor f in there. So if we want to know the volume of the aquifer, and these are concentric cylinders like I've got here, then the volume is the outer area times the thickness. This is the thickness of my aquifer, minus the area of the inside, the reservoir, times the thickness. So we can say that the volume of the aquifer, we'll call that Wi, and we usually measure that in barrels. You could do it in cubic feet as well, but we usually use oil field units, is equal to this fraction F times pi times the difference in radii squared times the thickness times the porosity. And if you know all those, then you can calculate the volume of your aquifer in barrels or cubic feet. And so we'll use that. Okay. Any additional questions? Okay, well, let me know. Okay, so let's go back to the material balance equation. This probably looks familiar to you all, right? If it doesn't, then that's even more of a reason you to go back and watch that summary video. But the material balance equation is something that reservoir engineers use to make predictions about the original oil and gas in place. And that's effectively what the GFGI and the NFOI are, right? So that's the free gas in place in standard cubic feet. This is the free oil in place in stock tank barrels. EGWF and EOWF are fluid properties. They're related to things like formation volume factor. F is the amount of fluids we produce. So I wrote it out here, but it's basically the amount of gas, oil, and water produced, and they're weighted by some fluid properties like formation volume factor. The one thing that at least I don't cover much when I teach Reservoir 1 is WE, the cumulative water produced. I might do a little bit with it. I might just give you WE, but WE is the amount of water that comes in from the aquifer into the reservoir. And we haven't done much with that in the past. So it's the cumulative amount of water. It's measured in barrels. You can imagine that it's a function of time. Right? At early times, you've got nothing, and then more and more water encroaches, so that changes with time. And it encroaches because of the pressure difference. So anytime we think about the flow of fluids, think that fluids generally flow from high pressure to low pressure. Okay, now you can get into things like capillary pressure, which complicates that a little bit, but at least at a large scale, it's that pressure difference that drives flow. So when the reservoir pressure drops, and the aquifer pressure is greater than the reservoir pressure, then flow, it goes from the aquifer into the reservoir. And then when that happens, flow of oil goes from the reservoir into the wellbore. So you can estimate this WE from the material balance equation. So if you get F, and that's fairly easy to get because you're obviously keeping track of how much oil, gas, and water you produce. In fact, that gets published publicly online. If you happen to know your original gas and oil in place, then you can back calculate WE. But there's another way to do this, and it's important because sometimes you don't know your original gas and oil in place. You want to find that out, is to estimate that from an aquifer model. And that's really what we're going to spend the next week or two talking about, is these different models for predicting WE, the total amount of water that gets encroached into the reservoir. These models vary by complexity and accuracy. You can imagine the simple models are the least accurate, the most complex models are the most accurate, and depending on what you want to do, you might use a simple model versus a complex model. Or what I like to do is do the simple model first, get a rough idea of what it is, and then, especially if it's worth pursuing, then I do the more complicated ones. So let's start with the simplest model. The simplest model is called the small pot aquifer. And so what it says is that the water influx, WE, again, that's the cumulative amount of water in barrels, is equal to the volume of water in the aquifer times the compressibility of the water, CW, plus the compressibility of the rock. They both contribute. Notice that there's no oil or gas compressibility in this equation because you've got no oil or gas in the aquifer. And then that's times the pressure difference between the initial pressure minus the aquifer pressure. Okay, or really PA is the pressure at the reservoir aquifer interface. So it's that driving force. Okay, so what does this mean? When you the first thing I notice is that it doesn't matter. This is the cumulative amount, meaning that if I waited for an infinite amount of time, theoretically, that this would be the amount of water produced. That number is less than WI. So every drop of water in the aquifer does not come into the reservoir, right? And that's completely analogous to what we learned in Reservoir 1, which is every drop of oil in a reservoir doesn't get produced. It doesn't matter how long you produce it in primary recovery. In the same way that if I shake up a soft drink and I open up the can, some of it comes out, but not every drop comes out, right? It's related to compressibility. And in fact, if you had zero compressibility, then you wouldn't get anything out, right? But you do have some compressibility of the formation in the water, and then you've got this pressure difference. Okay, this is the simplest and the least accurate of all aquifer models. It does represent the total amount that would come in if you had an infinite amount of time, but it doesn't include any time dependence in there, and that's important. And one of the reasons that's important is that in reality, the pressure of your reservoir or your aquifer reservoir interface changes with time. So this term would really change with time. And so you need to account for that. That's what I said next. Some of the things that are initially known as WI, right? We just learned how to calculate that on a previous slide. And WI is given here, right? So it's the same thing we had over there. So your compressibilities you could measure. So what you would probably do is if the compressibility of water is pretty well known, and compressibility of rock is, they're usually in the order of 1 × 10⁻⁶. But if you have a core sample, probably from your reservoir, not your aquifer, but if you have a core sample, then you can measure the compressibilities of both the rock and the water. You'll have a good idea of what your initial pressure is, right? You'll have pressure gauges in your wellbore that you drilled, and you might have a good idea of what your pressure is in the reservoir, at least at any given time. So you can calculate WE this way. One thing is that we as engineers like to use dimensionless equations from a lot, right? And we like to do that because those equations are appropriate regardless of what your conditions are. It doesn't matter what your compressibility is and things like that. And then you can make plots and things like that are more generic. So I wanted to show that. So if we put in our equation for WI, right? So WE is WI times, I'm calling it CT now. That's the total compressibility, the formation plus the water compressibility, times the pressure drop. Well, I put in my equation for WI, and this is my equation. Then what I do is I divide through by F pi H phi CT times the pressure drop, and then on the right-hand side, I'm just left with RA squared minus RE squared. Then what I'm going to do is I'm going to divide by 2 times RE squared on both sides. So that's why you can see a 2 RE squared, a 2 RE squared. And then what you can see is that RA squared over RE squared is given by this, and RE squared divided by RA squared is 1. So this term right here and this term right here are both dimensionless. You can plug in the variables and you'll see that they are dimensionless. In fact, it's pretty easy to see on the right-hand side. The radius of the aquifer and the radius of the reservoir both have the same units, right? They're feet. Or Or you can write this in the simplest terms as WED, the dimensionless water encroach, is equal to the dimensionless radius squared minus 1 over 2. And that's a nice simple formula for doing that, where WED is given by this formula over here, WE divided by U, PI minus PA, and U is given by this equation, and then RED, we already learned, is the ratio of the aquifer and the reservoir radius. So, if you think of any questions, don't hesitate to ask, but we're going to do an example problem together now. So if you haven't already, download from Canvas the example problem. I've got it up on the screen here as well. Make sure you got a pencil and a paper and calculator available, and we're going to try to work on this together. Okay. So what we have is a field with a water drive. So it's got an aquifer. The PVT data is given. So we have things like formation volume factor of the oil initially, and at the bubble point we got the solution gas ratio. I'm not sure if we're going to need it, but maybe we will in a future problem. The aquifer radius is 275,000 feet. So that's sounds pretty big, right? And then we assume that the pressure at the aquifer reservoir interface is 2430 psi. And I say use a small pot aquifer to compute the dimensionless cumulative water encroach, WED. So we just learned that WED is equal to RED squared minus 1 divided by 2. So that's a simple equation, but what we need is RED, which we don't know. And RED is equal to RA over RE. Well, RA is given, that's 275,000 feet, but I don't know RE, that's the radius of the reservoir. Okay, and so what I'll do is I'll give you a minute or two to think about it. And I might be calling on some of you by name, so if you think for a second about how you think you might calculate the radius of the reservoir given some of the properties that are in the table there. So the area is the bulk volume of the reservoir, VB, divided by the thickness, H. Both of those are given in the table, so the bulk volume is 73,590 acre feet. The thickness is 31.8 feet. And if I divide those, I get 2314.15 acres. And then we want to do our conversion factor. This is a conversion factor you'll want to probably memorize for the rest of your life. If you're going to be a petroleum engineer, you should probably know that there's 43,560 square feet in an acre. If you forget, then it's on my unit conversion table on the equation sheet. So that's why I tell all of our graduates to take those equation sheets and put it on their corkboard in their office. And if they ever forget something like a conversion factor or an equation, it's nice and handy there for them. Okay, and if I do that, I get 1.008 times 10 to the 8th feet squared. That's the area. And Caitlin, how did you say we calculate the radius from that?
The radius is the square root of the area divided by pi.
Right. So area is pi RE squared. Therefore, RE is the square root of A divided by pi, which is 5664.5 feet. Okay, so I will stop there and let you work on the next part of the problem, which I think is a little bit more straightforward. So let's calculate WED. That's the dimensionless amount of water encroached into the reservoir. So WED would have been RED squared minus, yeah.
Oh, yeah.
So how did you do that?
275,000 over 5664.5 for RED,
Yeah.
and then that squared minus 1, and then the answer for that was 1,177.95 dimensionless.
Good, that's what I got. And you're right, it's dimensionless. There's no units here, that's important. And so if you had actually divided 275,000 divided by 566.4, I got 48.55. So if you did that intermediate step there. Okay, so this is the dimensionless amount of water encroached, and you know, that number might be useful, but what we really want is how many barrels of water have done that. So now we got to put it in dimensionless terms. So that's what part B is. And WE is equal to WED U times PI minus PA. And so we know WED, that's given. The initial pressure is given as 2532. PA is given as 2430. The only thing we need to do is calculate U. So I'll let you calculate U, and you'll want to put those in their proper units of barrels per PSI. I'll give you a hint. So the equation for U is on the slides. If you want to look at those and calculate U, and then from that you can calculate WE. Really give a good handle on what typical values of fluid and rock properties are. So the water and the formation compressibility tend to be on the order of 10 to the minus 6 PSI, inverse PSI. Compressibility of oil, not surprising, is a little higher, so it tends to be like 10 to the minus 5. And then of course compressibilities of gases are much higher, so they could be 10 to the minus 3, so a couple orders of magnitude higher. So, and then you're going to want to do a unit conversion to put it into barrels per PSI. So remember, 1 barrel is 5.61 cubic feet. And what did you did? Let me see if somebody else. I'll call on Paige Campos. Did you get you by any chance?
I just realized I made a typo.
That's okay. Okay. Well, I'll tell you what I got. I got 15.92 barrels per PSI. Is that what you all got, or did I make a typo myself? Okay, I'm getting some nods, so that sounds like I got it right. And then WE is simply going to be WED U PI minus PA, which we know is 1177.95 times U, which is 1415.92 barrels per PSI. Good to put in our units so we don't make a mistake there. And the pressure drop is 2532 minus 2430 and PSI. And I get a really big number, 170,123,871 barrels. Is that a number that some of you got as well? Okay, I'm getting a few nods, so that's good. That's a really big number, but this aquifer is huge. And in fact, you know, it's called a small pot aquifer, so I suspect that this model's not adequate for this aquifer. But it's a good, quick way to get a ballpark number. And the aquifer is gigantic. I mean, we're talking about a radius of 275,000 feet. What is that? I think that's about 50 miles, right? 5,000 feet in a mile. That's 50 miles. That's a huge aquifer. So there was a question earlier, which was a really good one, which is, you know, the wellbore is small compared to the reservoir, but is the reservoir really small compared to the aquifer? Maybe not as much so, but sometimes you could have these huge aquifers, and you know, at 50 miles is pretty big, whereas maybe your reservoir in this case was 5,000 feet, which is almost a mile exactly. So it's a ratio, and we already saw it, I think, is a ratio of about 50. That was what RED was. And yeah, it's a ratio of about 50. So the aquifer is 50 times longer than the reservoir. And then, you know, for in terms of area, it's pi r squared, so you're squaring that. So a really big volume of water. And this would be theoretically the amount of water that would eventually encroach into the reservoir over very, very long times. But we know nothing here about the time dependency, and that's important as well. Any questions about this example problem? So this is pretty straightforward, but we'll get more complicated. And so I will go to the next model. So this model is I'm going to mispronounce it. I call it the Slifthus steady state method. And it is a very old model, right? So 1936, this was created almost 100 years ago. And it does include time dependencies. And so if WE is the cumulative amount of water, then dWE dt is the rate of change, so it gives some time dependency. And the assumption here is that the rate of water influx, you can almost think of it as like Q, right? Because when we talked about oil production, we would say QO or something, and that's rate, the amount per time. And this is a rate, a rate of water influx with respect to time is equal to some proportionality constant, K prime, which we don't know. I put the prime in there because I don't want you to think it's permeability, right? We often use K for permeability, and it's not. So we put the prime in there. We run it. We use so many variables in engineering, we run out of variables, so we got to start adding superscripts and subscripts. But K prime is just some constant which we don't know. Pi is the initial pressure, and P is like a reservoir pressure, or is a reservoir pressure. And that changes with time. Okay, so that reservoir pressure will change with time. As you produce more fluids, the pressure is going to drop. So the time dependency is largely in P, the pressure here. So how do we estimate K prime? Right? We might want to estimate K prime based on historical production data, and then once we have K prime, we can use it to predict future production data. So if we've been producing the reservoir for a while, and we can determine WE from a material balance equation, then K prime is simply dWE dt divided by that pressure difference. And then again, once K prime is determined, it can be used to predict future water influx. So what you probably need to do, or you would need to do, is you would use your production data, use the material balance equation, calculate WE at different times, and then you can do a derivative, like a numerical derivative, like a finite difference of delta WE divided by delta T, right? And then once you've got that K prime, you can integrate that. So WE, the cumulative amount of water, is equal to K prime Pi minus P. And the reason why this integral is not so simple is that your pressure P is likely going to vary with time. It's going to decrease with time. But you might have that data. How do you have that data? Well, you've got a wellbore in your reservoir. In that wellbore, you almost certainly have pressure gauges. Those pressure gauges are going to tell you the reservoir pressure. And so you'll have that. And so this pressure is a function of time. If it was a really simple function, like a straight line or something, then maybe you can integrate this by traditional methods. If not, you can do it numerically. You all took PGE 310, probably with Dr. Foster, maybe Dr. Pradanovich, and you probably learned how to integrate numerically using methods like the trapezoidal rule. Am I right? Does it sound familiar at all? Okay, you could do that here. So if you now know K prime, you know Pi, and you've got pressures at different times, you could calculate that numerically in a spreadsheet or in a Python program or something like that. So I will finish up with one more slide and talk a little bit about other ways to calculate this K prime, the water influx constant is what I'll call it. And if we recall the material balance equation for an oil reservoir, so there's no gas, so that's why I don't have the G term in there. So N is the original oil in place. EOWF, we call that the expansivity, is related to the fluid properties. WE is that cumulative water produced, and then the right-hand side is the oil and water produced multiplied by their formation volume factors. If we take the derivative of all terms in that equation, then what we get is EOWF dN dt plus DWE dt plus BO dNP dt plus BW dWP dt. So we just took the derivative of all terms there. Now, as I noted on there, dNBT is dNP dt is the change in oil produced with time. That's the oil rate. Okay, and nobody's going to produce oil from a reservoir without mentioning the oil rate or the water rate for that matter. So dWP dt. So you'll have a table, you'll have data of QO and QW versus time. dN dt, N is the original oil in place. That's how much oil was there originally. That doesn't change with time. The amount of oil there might change with time, but the original oil is by definition a constant. So dN dt is 0. So then dWE dt is given as QOBO plus QWBW. I should likely have some PVT data. And then you can make a plot, right? And you can make a plot of dWE dt versus the right-hand side and the slope, and from that you can calculate K prime. And we'll do an example on that most likely Monday. This was for an undersaturated reservoir. You can tell because there's no gas term in there. There's no GFGI. But you could do the same exercise for a saturated reservoir, meaning we've got both an oleic phase and a gaseous phase present. I think I'll stop there.